All right, everybody. Welcome to our last lecture. Reminder to everybody, the final exam is going to be next Tuesday. So I'll be sending out some more emails, but as I've already mentioned before, 3 hours, 9 a.m. in this room. And it's going to be 8 problems, very much like the problems you've already seen on the first 2 exams. The difference is you may see some circuit topologies that fit in with some of the stuff you're turning in with this last homework assignment. So for example, if you see a cascode amplifier or a differential amplifier topology, don't be surprised. So I want you guys to be aware of those. But on the other hand, there's nothing I'm going to give you that you cannot figure out by using the large signal and the small signal equations. That's entirely the point we've been trying to get across in this semester is no matter what you see, if you understand the analysis technique, then you can figure it out. And that's ultimately what this class is all about. So let's begin. First of all, are there any questions before we get started? So exam number 2, I will have that available for you guys. I'll email you as soon as it's available for pickup. Some people did very well on that exam. Congratulations. So I'll have complete statistics once the grading is complete. Also a reminder to everybody, I need to have your lab memos turned into me, emailed to me by tomorrow, and of course the last homework as well. So a lot of work for which I apologize, but that's the end of the semester. There's not much we can do about it, especially when you got a lab and a lecture. So, any questions? All right, then let's begin by looking now at our very last chapter, and that is the differential amplifier. And this kind of wraps up all the basic stuff we want to look at in this class. So, past this class, if you want to go on and see more advanced circuit concepts and learn more about circuit design, I would very much recommend EECE 4380 next semester from Dr. Massengill, the Electronics 2. So if you've enjoyed this class and you say, this is really neat, I want to learn more about circuits, take Dr. Massengill's course. I highly recommend it. He will go into a lot of this stuff in more depth. You'll see the same kind of amplifier topologies, but he's going to look at issues we didn't look at. Specifically, he's going to look at, for example, frequency response. He's going to look at feedback mechanisms and so you can learn how to analyze those. And he actually has a pretty comprehensive design project that's part of the class itself, which is a really good kind of working with your partner and try to design an advanced circuit. So I cannot recommend this highly enough. I think it's a great class. Analog circuit design is a great subject to learn because I always tell people, if you learn analog circuit design, you will never lack for employment in your entire career. Professor Massengill and I joke about the fact that even after we retire, we'll still be able to go out and work someplace as an analog circuit designer because that's how much in demand they are. So just something to consider. If you think this is interesting and you've enjoyed it and you've learned a lot from it, it's a great career. Pursuing circuit design is a great career to do. So I hope that I've kind of lit the fire in some of you guys to kind of go down this path and pursue this. It's a really neat topic to get into. Okay, so let's talk about the differential amplifier. And we can really say this is the 4th fundamental amplifier topology. The difference is, unlike the other amplifier topologies we looked at, we need a minimum of 2 transistors to make it work. But it is used everywhere, the idea of the differential amplifier. It has some very important advantages. First of all, it is less sensitive to noise and interference than the single transistor amplifier topologies we're already familiar with. So when we think about common source, common emitter, common gate, common base, common drain, common collector, those single transistor topologies we're already familiar with, as we're going to see, there's a very important property of the differential amplifier that makes it a lot less sensitive to noise. And most important, as we're going to see, it's very well suited to DC coupled multi-stage amplifier designs. So let's look at the differential amplifier, and we're going to start by looking at the most basic topology. Now I could do this with either BJTs or MOSFETs, but since MOSFETs are really more common and the small signal diagram is a little bit simpler, we're going to start with MOS differential. Let's look at what's called the MOS differential pair, which is the simplest form of a differential amplifier. So here's the MOS differential pair, which consists of two transistors. And for the sake of simplicity, I'm going to assume we have an ideal current source we have connected here. And I'm going to have two resistors, R sub D. Now, what's interesting about this design is it's symmetrical. So in this case, we are assuming M1 and M2 are matched, and they have the same width to length ratios. Also note, the two drain resistors, R sub D, same resistance. So this is basically kind of a mirror symmetry between these two inputs. But notice the two sources of the infets are connected together, and they flow through this current source with a value of I. And we have a name for this. We say this is the tail current source. You'll hear that term, the tail current. And where does that name come from? Because people thought it looked like a little tail on the end of the diff amp. So it's called a tail current. All right. Now, we're going to make some assumptions. First of all, since this is an amplifier, I'm going to assume that M1 and M2 are saturated, which is a reasonable assumption to make. And let's assume that VG1 and VG2 are the same voltage. So let's set them to the same potential. Well, if VG1 is equal to VG2, and they share the same source voltage, then let's go ahead and I'm going to put in VGS1 and VGS2. So So if VG1 is equal to VG2, and they have the same source voltage, what must be true? VGS1 must therefore equal VGS2. Now, if VGS1 and VGS2 are the same, and if the two transistors are both in saturation and they have the same geometries, what must be true about their drain currents? Got to be the same. So these currents, ID1 and ID2, must also be the same. Same drain currents, same gate source voltages. However, we note that ID1 plus ID2 must be equal to I. Therefore, the only way we can make that work because of that tail current source is for ID1 and ID2 to both be equal to I over 2, the tail current source divided by 2. So I've got a completely symmetrical situation here where I've now got I over 2, half of the tail currents flowing through both sides. Now, the resistors are the same. I'm connected to the same power supply at the top. Same currents flowing through both resistors. What must be true about VD1 and VD2? They've got to be equal too, right? Same current, same voltage drop, therefore VD1 and VD2 are equal. So both VD1 and VD2 must be equal to VDD minus 1/2 I times RD, right? So I've got a symmetrical situation. The voltages and the currents on both sides are symmetrical. So let's think about this. Let's look at that circuit for a moment. Notice that VG1 and VG2, I did not specify a value for VG1 and VG2. I just simply said they were equal. That's all I said. Let's assume they're the same voltage. As long as VG1 is equal to VG2, we can increase those two gate voltages or decrease them. We can change them. And the drain voltages at VD1 and VD2 and the drain currents will not change. So the drain voltages and the drain currents will still remain equal to each other. Now this gives us an interesting phenomenon here. A change that is common to both inputs results in no change in the drain currents or the drain voltages. So a common input voltage at both gates All right, well, we take this idea of the common input voltage. There's a specific name we give to that. A condition where VG1 and VG2 are equal is a common mode input. We say that a differential amplifier rejects a common mode input voltage. And what do I mean by that? I mean a common mode voltage can change, but nothing happens at the outputs. In this case, we're considering VD1 and VD2 to be the outputs of this amplifier. So a differential pair rejects any changes in a common mode input signal. In other words, i.e., VD1 is equal to VD2, and they do not change. So in this case, we're considering VD1 and VD2 to be the outputs of the differential pair. Okay, everybody see this, understand this. Now this is a really powerful property of a differential amplifier. And here's the reason why. It doesn't matter if VG1 and VG2 are DC voltages or if they're DC voltages with an AC component. So for example, let's consider this differential amplifier. There is a really kind of ubiquitous noise source, AC noise source in this room right now. In fact, it's just about in every place you will go. Can anybody tell me what that noise source is? 60 hertz. 60 hertz AC. You can actually hear that on a cheap AM receiver, right? You can actually hear that humming noise. It's very easy to pick that up on audio equipment, okay? So that noise is everywhere. That 60 hertz electromagnetic field is everywhere. Okay, so I've got an amplifier, a differential amplifier, and any input of any amplifier can pick up that 60 hertz noise, that field. So let's consider, for example, that I've got a 60 hertz field that's picked up by one input, and I've got that same 60 hertz noise that's picked up by the other input. What effect does picking up that 60 hertz noise have on VD1 and VD2? None at all. It rejects it. So as long as it's the same voltage on both inputs, I can be in a very noisy environment and the common mode signal is rejected. Nothing appears at the output. This is a really powerful property of differential amplifiers. Differential amplifiers only work on the difference between the two inputs, but common mode signals, you don't have to worry about. They get rejected. Yeah?
What is the source of the 60 hertz?
Oh, it's going to be the electromagnetic field from your power lines. In other words, think about it. That 60 hertz coming out of the wall is not just electricity, it's electromagnetism, okay? You can easily pick that up. If you ever take, for example, and have an electric amplifier and unplug it and just wave around a fluorescent light, you'll hear that hum. You'll easily hear it. That's a real interference problem you'll have, for example, for high-end audio. So that's everywhere. It's everywhere. I mean, there are plenty of other noise sources, but this is the one that we're all very commonly used to because we literally are living in a 60 hertz electromagnetic field, all of us. All right. In fact, 20 years ago, 30 years ago, one of the big health scares people were worried about was that the 60 hertz electromagnetic field in your house was making you sick. And so people were really worried about that. And my friends and I thought about marketing an electric blanket rectifier to turn the AC to DC in your electric blanket so it wouldn't make you sick. And we were thinking, of course it's totally bogus science, but hey, it would have made a lot of money. But we were being engineers and being ethical, we decided we wouldn't do that. But there's a lot of weird things people worry about, and that used to be one of the things people were really worried about, okay? It was that 60 hertz electromagnetic fields would make you sick. Now, what else do we hear about nowadays? Just a little bit of an aside here. Everybody remember how Wi-Fi would make you sick? You might remember that 15 years ago. What's making you sick now, supposedly? 5G, okay. The same arguments keep coming along with people trying to sell the same snake oil. It's just that the frequency changes, okay? And then once we get used to the new technology, then everybody says, oh, it's fine. All right. Oh, but this next one's going to kill you. And so we had it with 4G. 4G was going to make us all sick and kill us. Well, it didn't kill us. 5G is now going to make us sick and kill us. No, it just moves right along. So somewhere along the line, somewhere in your lives, guys, you're going to hear someone claiming that some new technology coming along will kill us all. All right? You can take that with a very large shaker of salt. Take it from me. Okay, you need to think very skeptically about this stuff because what's true about all these types of electromagnetic fields? They're non-ionizing. Okay, it's not like it's going to mess up your DNA. The worst it can do is heat up your tissues. Okay, so don't stand next to a 100,000 watt transmitter tower. You can actually get heating like in a microwave oven. But beyond that, you're fine. Now, what will give you cancer and make you sick? Going out in the sun, sunbathing, that's ionizing radiation. But people don't seem to worry about that. I tell you, risk assessment by human beings is a weird thing. People freak out about nuclear reactors and they send their kids outside to play in full view of a nuclear fusion reactor that causes how many tens of thousands of skin cancer and people die from that every year? We should shut down the sun. It's clearly dangerous. So anyway, a little bit of an aside there, okay? All right. So, from a differential point of view, from a common mode point of view, nothing changes. But now let's look at the more interesting case. Now, there's a common thread here that I have not mentioned. In order for all of this to be true, what must be true about the operating conditions of those two transistors? They've got to stay in saturation. But if I raise and lower VG1 and VG2, there are limits to how far I can go before that's no longer true. So let's consider what those limits are going to be. Oops. So we note that M1 and M2 have to remain saturated. And if we think about VG1 and VG2, there's a limit to how high and how low they can go. I mean, obviously, if you think about it, if I have VG1 and VG2 less than ground, then obviously I'm not going to be able to keep those transistors turned on because VGS is going to be negative. But actually the limits are less than that. And let's actually sit down and let's calculate what those limits are. VG1 is equal to VG2, so what are the values of VG1 max and VG2 max and VG2 min and VG1 min such that the transistors remain saturated? All right, let's go through and let's apply a little math. All right, so let's think about this. Let's first assume that we increase VG1 and VG2. I'm going to say VG1 is equal to VG2, and I'm going to call them VCM, the common mode voltage. So we're going to start increasing the common mode voltage. As we increase the common mode voltage, VGS1 and VGS2 have to stay the same because the currents aren't, we don't want the currents to change. They can't change. And therefore, Vs also increases. So looking up at this diagram here, I'm increasing the voltages at the gates, so the source voltage, V sub S, has to increase as well. Because VGS1 and VGS2, I'm assuming those can't change. Currents aren't going to change. So in this case, what's going to happen? So as Vs increases, VDS1 and VDS2 decrease the drain source voltages across those two transistors. So those drain source voltages have to decrease. And what happens is I decrease the drain source voltage across a transistor that's in saturation. What eventually happens is the VDS gets smaller and smaller. I'm going to hit triode region. Okay? So I'm going to do that until we reach the saturation triode boundary. When's that going to happen? What's the boundary condition? VDS is equal to VGS minus VT. We all remember that. Or I can drop the source voltage. VD is equal to VG minus VT at that boundary. Or VG is equal to VD plus VT. So that must be the boundary condition between saturation and triode. Okay, so what is my VCM max? The maximum common input voltage must be equal to the threshold voltage plus VD. And what did we say VD was equal to? VD was equal to VDD minus 1/2 I times R sub D. So that's the maximum possible voltage I can have at the gates. As they both continue to rise, at some point I'm going to push M1 and M2 into triode. And we can calculate what that boundary condition is. Okay, now let's go the other way. Now let's reduce VCM. As VCM decreases, then VS decreases. Now, in order to understand how this circuit's going to work, I need to think about, and rather to understand the limits of how this circuit's going to work, I need to think about what I'm going to use to replace that tail current source. What is probably a very obvious device I'm going to use in place of that current source? How about a third transistor, right? Why not another transistor? Let's redraw this. So in this case, what I'm going to do is I'm going to assume I have some DC bias voltage, and I'm just biasing a third transistor, call this M3, excuse me. I'm going to bias that third transistor, and that's going to be my tail current source. Okay, so VCM decreases. VS decreases. As VS decreases, what happens to the drain source voltage of M3? That also decreases. Okay. VDS3 gets smaller and smaller. Now, I'm assuming as a current source, this thing has to be saturated. Once again, what's the boundary condition I hit? I hit the triode saturation boundary condition. Until M3, which is our tail current source transistor, that reaches the triode saturation boundary. Well, when is that going to happen? Okay, so if we think about that for a moment, then in this case, VDS3 will be equal to VGS3 minus VT. That's our boundary condition. What is VGS3? Well, it's that DC bias voltage, V bias. This is just a DC voltage that's biasing this transistor. So that's going to be equal to V bias minus V sub T. So in this case, VC min, and let me do this right here. Therefore, my common mode minimum input voltage, once I reach that limit, I have this voltage plus that voltage. So I've got my VDS3 plus my VGS1. So what's the minimum voltage that I can go for VCM? This boundary condition voltage plus the gate source voltage, which cannot change. And therefore VC min is equal to VGS1 plus V bias minus V sub t. And of course I could also use VGS2 in this equation because they're the same voltage. Doesn't matter. So whether I use VGS1 or VGS2, it's the same equation, same value. There's my minimum voltage. Now you notice, guys, how I threw a totally brand new concept at you. And yet, if we understand the DC equations and we understand saturation and triode, you can see for yourself how to derive this. You can calculate these limits yourself. So I want to point out, nobody sits around and memorizes these equations. You want to be able to derive them. You want to be able to write the equations and figure out for yourself where are you hitting the limits of your design. Now incidentally, this VCM max, VCM min, we call this the common mode input range. CMIR. This is the range over which all transistors remain in saturation. Okay? So, we now understand how the circuit works with a common mode input signal. But common mode signals are not very interesting. We want to amplify a difference between the two. We want to amplify some kind of signal, which is the difference. And you think about how op amps worked. It was the same thing. So what we're going to do now is we're going to consider the effect of a differential input voltage. Okay, so let's go back to our original circuit. Okay, so in this case, I'm going to have VG1 and VG2, but now we're going to assume they're not the same voltage. So VG1 is not equal to VG2. I'm going to define a voltage, VID, as the differential, yes?
You currently have the VG2.
Oh, I'm sorry, this should be VG1. I'm sorry, thank you very much. VG1, M1, and M2, thank you. Okay, so in this case, VG1 and VG2 are not the same. And yes?
Should we still assume that M1 and M2 were matched with the same like WL ratio?
We're assuming nothing's changed. Okay, so we still have the same circuit we had before, only now we're going to make the two voltages different. All right? What is going to happen to the circuit? Well, in this case, I'm going to define VID, which is the differential input voltage, as the difference between those two voltages. It's VG1 minus VG2. Therefore, if VID is equal to VG1 minus VG2, therefore VG1 is equal to VG2 plus VID. I'll just go over here and define it that way. This is equal to VG2 plus VID. All right, so let's think about this. Both transistors still have the same source voltage, but one of them is going to have a larger VGS than the other. So we note if VID is greater than 0, if we assume VID is a positive voltage, then VGS 1 will be greater than VGS2. That makes sense to everybody? So if VGS1 is greater than VGS2, what must be true about the drain currents? ID1 must be greater than ID2. But here's the trick. ID1 and ID2 are still equal to I. They still total to I. So what's going to happen is, as I1 increases, I2 is going to decrease, because that's the only place ID can get extra current from because of that current source is by taking it away from ID2. ID1 will increase until it reaches a maximum value of I. ID2 will tend towards 0 as we increase VID. Until finally, all of the current's flowing through one leg and not through the other. Now, the book goes through some derivations. I'm not going to bother to go through the math, but you can actually do that for yourself. But what you'll find is VID will be equal to the square root of 2 times I divided by K prime N times L over W when ID1 is equal to I and ID2 is equal to 0. So that's your condition. That's how large VID needs to be. And the book goes through some derivations. I'm just going to skip them now for the sake of time, but you can prove these to yourself. And it also turns out that you can do a little more math. We can also show that VID will actually be equal to the square root of 2 times the overdrive voltage. It turns out if you factor out that square root of 2, the remainder, you can do some algebra with that and prove to yourself that it's equal to the overdrive voltage for M1 or M2. So same expression. Same thing. All right? So you can actually plot this interaction between these two. And the book's got a nice little graph you can see. Where you can actually plot the ratio of drain current to I as a function of the differential input voltage. When VID is equal to 0, then the ratio of each drain current to I is just equal to 1/2. Each transistor has half of the current. And I can draw this nice little set of plots here. And so this is ID2 over I. And this is ID1 over I. And the boundary, we hit the boundary here at the square root of 2 VOV and at minus the square root of 2 times VOV. So I can make that differential input voltage positive or negative, and at these limits of plus or minus the square root of 2 times the overdrive voltage, I will have all of the current flowing through one side of the diff amp and no current flowing through the other. Well, it turns out there's a nice linear region in here. Okay, I didn't draw it very well, but there's a linear region before we start hitting the saturation or cutoff boundaries for either transistor. And what can we do with nice linear regions? We can make amplifiers out of those nice linear regions, right? Okay, so what we're going to do now is we're going to take this circuit, except now we're going to think of it from the small signal point of view. This is kind of a large signal point of view we're doing here, but we care about the small signal behavior. So what's that circuit going to look like? What I'm going to do here is I'm going to express VG1 and VG2 in terms of their common mode voltage, the same voltage, the common voltage between them, plus the differential component. And what I'm going to do is I'm going to say VG1 is equal to some DC common mode voltage plus 1/2 of the differential input voltage. Over here I'm going to say VG2 is equal to this common mode DC voltage minus 1/2 the differential input voltage. Notice what I did here. I took that differential input voltage and I split it between the two inputs. So instead of having all of it on one side, I'm just splitting it between the two, so half is on one side and the other half is on the other. And as one rises, the other falls. So just mathematically, I'm expressing this a little bit differently between those two gate voltages. Okay? We note also that ID1 and ID2, which is our DC biasing, must be equal to I over 2. So from a DC bias point of view, the drain currents have got to be the same, right? That's how we're biasing this circuit. And so the differential input voltage is the AC component that we are injecting that's riding on top of the DC common mode voltage. All right? So if ID1 and ID2 have the same DC bias, and if M1 and M2 are matched devices, what must be true about the transconductances of those two transistors? They're the same, right? And therefore, GM1 is equal to GM2. The transconductances on both sides will be the same. All right? So I'm just going to call those GM. And therefore, I'm now going to take this and transform this into a small signal diagram. Now, to make things simple, I'm going to ignore R sub O. Now, referring to this, I'm going to now define the following, guys. Remember how I said the drain voltages were the output? I'm now going to define VOD, the output differential voltage between those two drains. So in this case, I'm going to define VOD. So VOD is just equal to the difference between those two drain voltages, VD2 minus VD1. All right? So in this case, I'll have that in the diagram. Notice the source has nothing connected to it. That's an ideal current source. That becomes an open circuit. Now the common mode voltage, I assume that's DC. I'm zeroing out that DC. The power supplies, I zero those out. And this is all that remains. So in this case, this is equal to GM times VGS1. This is equal to GM times VGS2. And we note here in this case we're ignoring R sub O. And now we can go through and write our gain equations for this. And so what we're going to get is that VGS1 is just equal to VID over 2 minus VS. VGS2 is equal to minus VID over 2 minus VS. We also note, in this case, and once again I'm still defining my VOD, we also note that these two currents must be equal to 0. So that's the KCL equation for that VS node. So my KCL at VS is this. Something very interesting happens. The GM VID over 2 and the GM minus VID over 2 cancel out. And if we solve for this, guess what we find out that VS must be equal to? 0. So VS is equal to 0 volts. What is interesting about that? That is a small signal voltage of 0 volts at the source of both of those transistors. Where's the capacitor? There is no capacitor. Do we need a capacitor? No, we don't. And yet I can get a virtual ground, a virtual 0 volts at the source. This is a virtual ground. I can now get that source voltage at 0 without the need for a large capacitor. That is really useful because now we've gotten rid of one of the things that limits the gain. We don't need that capacitor anymore. That's extremely powerful. Okay? Now we can go through and I can now write the KCL equations at the two drains. And so in this case, VD2 over RD, this current plus that current must be equal to 0. And in addition, that's VD1, excuse me, I got those backwards. That's VD1 over RD plus VD1 is equal to 0, excuse me, for the first one. And for the other, VD2 over RD plus GM times minus VID over 2 is equal to 0. So these are the KCL equations for the two drains. And in this case, I can show that VOD is therefore equal to VD2 minus VD1. So I can go through and I can show in this case that VD1 is equal to minus GM times RD over 2 times VID, and VD2 is equal to GM times RD over 2 times VID. And the difference between those two is therefore going to be equal to GM times RD. Pardon me, I should say VOD. I wrote that incorrectly because if I'm going to incorporate this, I have to also include VID. And so therefore, VOD over VID must be equal to GM times RD. There we go. So I've got a gain, which is a function of the differential output over the differential input voltage. What does that GMRD remind you guys of? It's a common source amplifier. In fact, let's think about this for a moment. The differential amplifier results in a small signal voltage of 0 volts at the source. What is that if I've got 0 volts? It's a common source amplifier. It's a common source amplifier. It's just two common source amplifiers, each with half the gain, but when you combine them together, we get the full gain. Except, I didn't need a capacitor at the source. I only did it with transistors. That just saved me a whole lot of money, which is one of the reasons why this topology is so incredibly popular. Now, normally we don't like to use resistors. We want better loads. Well, what kind of loads have we looked at in place of resistors when we looked at the basic gain cells? Current sources, yeah. So really, nobody uses these types of circuits with a resistor. Instead, we have current source and current mirror loads. So differential amplifiers, we normally want active loads. What do I mean by active loads? Current sources. So here's one way to do it. So in this case, I'm replacing the two drain resistors with two transistors biased as current sources. A couple of PFETs as current sources. Now I can go through and do the small signal diagrams. The difference is now what resistance do I see looking up into the drain of that current source device? What's it going to be? It's going to be what? It's a little R sub O, isn't it, right? It's the output resistance, the R sub O, 1 over lambda ID. And so we can show and in this case, we can go back and do the same small signal diagram I did before, except these are going to become R sub O's, and I also want to now include the R sub O's of the other transistors because now they're not negligibly large compared to the others. But we can show now that this is true. That VOD divided by VID is equal to GM1 times R01 in parallel with R03, which is also equal to GM2 times R02 in parallel with R04. So I get a much larger gain because the small signal resistance seen looking into those transistors is now a lot higher than we had with just the resistor before, the R sub D. So we get a much higher gain. But there's another trick we can do with this. If I've got these two transistors, it turns out I don't need an external DC bias. There's another trick. I've got two PFETs. What can I do to those two PFETs? Let's connect them as a current mirror. Let's draw this circuit instead. We're going to let those two transistors, in effect, bias themselves via a current mirror. The difference now is I don't have symmetrical drains anymore. They're not connected the same. Instead, I've got one drain voltage, V0. That is a single-ended output. It turns out now that from each of these inputs, I've got a path from this input through here to the output. I've got a path from this input through here, through the current mirror to the output. The same thing is true with this input. I've got a path from here to the drain and a path through here, back around into the output there. So you actually have two paths for each of the small signal voltages to that single-ended output. But after a great deal of math, which I'm not going to bother to go through, you can prove it yourself. It's messy, but it's very doable. We can show that VO over VID is equal to, in this case, GM1 times RO1 in parallel with RO3, or equal to GM2 times RO2 in parallel with RO4. You look at that and say, well, Dr. Holman, it's the same gain as I had over there before. What's the difference, though, between this circuit versus that circuit? It's a single-ended output. This topology lets me go from a differential input to a single-ended output, which I can then feed into my next amplifier stage. So we can carry a differential signal through various amplifiers, or a diff amp lets us convert from a differential to a single-ended voltage. Very, very handy. Extremely, extremely common topology. You'll see variations of both of these topologies all the time. Okay? So, given this, we've got just a couple of minutes left. I'm going to design an op amp. I'm going to show you guys how to build an op amp. I start with a diff amp, because keep in mind, an op amp has got a differential input, Vp minus Vn. And so this will be Vn, this will be Vp. I put it through a diff amp. I've got a current source transistor to bias it with. I'm going to take the output of this, and I'm going to then feed it into a common source amplifier built using a PFET. What's the purpose of this? To get me lots of gain. And then finally, I'll go through a common drain amplifier or a source follower. What does that give me? It gives me my low output impedance. So I only have a gain of 1 here, but in this case I get R out is low. I now have a high input impedance with a differential input voltage. Now notice, in each of these cases there is a transistor acting as a current source. Hey, let's take all of these and let's connect all those gates together. And then let's go over here and connect them to a circuit to bias them all together. There's your bias circuit. That is a simple, this is called a Miller op-amp circuit. That is a simple op-amp. Anybody can build that. It works actually pretty well. There is a piece here missing, which is beyond the scope of this course. You have to add what's called C sub C is a compensation capacitor. The purpose of a compensation capacitor is to set the bandwidth. It causes this op amp to act like a single pole system. And if you haven't had circuits 2, you don't know what I mean by single pole, which is why you need to have circuits 2 to take electronics 2, because we're going to talk about poles and zeros. But if you've had circuits 2 and you know what a pole and a zero is, then you understand when I say a for a single pole response. It turns out that is necessary to make sure your op-amp is stable and it doesn't oscillate. So I've taught you all the rest of it. What I can't teach you is that. That's the next class. But this is how you do analog design, guys. I put all these little building blocks, these pieces together. The trick is in making them work and interact together with each other. As long as you understand that, which comes with experience, you can design the most amazing circuits from just some very fundamental building blocks. But practice and expertise and time is what it takes. Okay? So I took you from nowhere to now you know what's on the inside of an op-amp. Now, a real op-amp is a bit more complex than this, but that's the basic topology. All right? I gave you the simplified version. There you go. You've gone from nothing to now knowing what's inside that little device you've been using and learning about since Circuits 1 and Circuits 2. Okay? I really hope you'll enjoy. Some of you will take and enjoy Circuits 2 next semester from Dr. Massengill. You'll follow up on all of this, but I hope I've got you all off to a good start. Good luck. I will see you on Tuesday on the final exam.